Hi, my name is Max Painley, and I'm a robot test engineer here at ATI in our material removal group. I have been working with our tools in deburring and finishing applications for several years over the course of hundreds of trials. Today, I want to discuss some tips and tricks I've learned over that time that can help you improve your robotic material removal cell. In this video, we will cover air prep setup, manipulating different tool settings, and programming tips to improve your finish and ensure long product life of your tool. With these tips, you should have a better idea of how to maximize your automated material removal process, and you will be better prepared to have a smooth integration for your cell. One of the main sources of issues when we troubleshoot applications is improper air preparation. Tube size, pressure drops, and incorrect pressure levels can all cause headaches that are difficult to see when looking at finished parts. Many users assume that since they are supplying shop air at 90 psi, the tool is getting everything it needs. That is often not the case. The size of the tubing is critical for the performance of the motor. When a smaller than recommended tube is used, it can choke the airflow, which interferes with the tool's performance. In order for the tool to operate properly, all of the tubing between the compressor and the tool should be at least as large as the required tubing size, which can be found in the tool manual. The tubing can be larger in diameter, but not smaller. This includes smaller tubing that uses adapters to increase up to the motor inlet diameter. Limited airflow can cause diminished power and speed. Streamlining the airflow and minimizing the number of fittings and adapters used can improve airflow as well. Each fitting and turn in the supply airline acts as a choke point and can result in pressure drops. Try to have a streamlined setup and eliminate any unnecessary right angle fittings, kinks, or reducing adapters. As you plumb your tool, make sure the airlines themselves do not restrict movement. The air port on most ATI tools is directly connected to the pivoting motor. If your airline is restricted, the motion of the tool can be biased to one side, preventing proper compliance motion. To make sure you have your air supply at a sufficient level, take readings of the air pressure and flow as close to the air motor inlet as possible. With possible unseen choke points and pressure drops, it is important to understand what air is actually getting to the tool as it runs. Here we see a 5 to 10 psi pressure drop when the valve is open to the tool, which is an acceptable amount. If you see a much larger pressure drop when measuring your system, assess your airlines and see if you can find any of the issues mentioned earlier. Measuring air pressure at the tool can be cumbersome, but fortunately, this gauge only needs to be placed during setup and can be removed for production once proper airflow has been verified. It is also vital to measure volumetric flow in this same manner with a flow meter. It is possible to supply the tool air at the correct pressure, but at low volume. Without proper volume, even if the tool can achieve proper speed, it may lack power and stall easily. Air quality is a critical factor as well. Air should be clean, filtered to 5 micron, and dry from water. Some tools in our catalog cannot have lubrication in the line, while others require it. It is important to supply the tool with properly prepared air. Otherwise, you risk poor performance or premature failure. Customers with tools that require lubricated air should make sure that they are supplying the correct oil type at the required rate. If you address these air preparation issues, you will maximize the life of your tool as well as the consistency of performance. Programming and setup of a compliant deburring tool is not difficult to get started, but there are many variables that you can adjust to improve your results. ATI will work with you to find the best tool for your application. However, once you have selected the robot, tool, and fixturing setup, there are still many settings that you can adjust to improve your finish. With so many variables, it can be difficult to identify which changes are affecting the finish and in what way. It is important to adjust one thing at a time to understand that particular setting's effect. Compliance pressure, feed rate, and burr size and shape are the major parameters that you can adjust to change your process. Let's take a look at how these affect finish. The built-in compliance in ATI's tools allows you to account for variation in part size, feature location, and amount of material removed. The force applied by the compliance mechanism to your part is adjustable on all ATI tools via air pressure. We always recommend starting at the lightest compliance pressure and increasing until you achieve the desired amount of material removed. When compliance pressure is increased, more material is removed and the motor is under greater load. The finish may be better because chatter is less likely. When compliance pressure is decreased, less material is removed, but more chatter may occur. If you're using a tungsten carbide bit and are removing too much material, you may want to consider decreasing the compliance pressure. Another factor to consider is feed rate, which is the speed of the robot motion. For the purposes of this discussion, we will focus on a process-to-part application, where the workpiece is statically fixtured and the tool is mounted to the robot. but know this information applies to part-to-process applications as well. If you find your finish is not smooth enough, you can decrease feed rate. This will increase the amount of material removed because the slower speed allows the tool more time to eat into the material. Each bite is smaller, resulting in a better finish. Conversely, if you need less material removed, you can increase feed rate to give the media less time to work the material. However, this will typically result in a rougher finish. Many process improvements come at the detriment of another. It's all about balance. The size of the cutting burr flute is another parameter that can have a great effect on the finish and material removal rate. Larger fluting will remove more material than smaller flutes because each swipe of the material is larger. These larger swipes will take off more material and result in a rougher finish than with smaller flutes, which take off less material and result in a better finish. While it may be tempting to choose every setting for the best possible finish, you may have cycle time constraints that demand you move faster or use fewer passes, reducing the ability to optimize finish. Another important detail about the cutting burr, or any other media, is its shape. The shape of the media can weigh heavily on access to certain features. When you approach a flat plane or external edge, it can be a straightforward task. As features become less accessible, or you need to approach from another side, however, consider changing your media shape to better access that feature. Just another thing to keep in mind as you keep setting up your process. The last parameter I would like to mention when talking about improving finish is cutting direction. The direction of the tool's path can affect part finish, secondary burr creation, and media wear. For all of our rotary tools, we recommend using climb milling, where the rotation of the burr is in the same direction as the feed direction of the tool. The burr motion should be similar to a car wheel rolling along with the car over the pavement. The burr rolls along, climbing up the raw edges of the part. This creates a smoother finish and allows for longer burr life. This is not always possible due to application constraints, but it is best if possible. The opposite of this climb milling is called conventional milling. This picture shows the secondary burrs that can be created when using conventional cutting. Both cuts were made with the same feed rate, compliance pressure, and cutting burr, but changing direction greatly affected the finish. While we're on the topic of tool direction, I would like to discuss other path programming considerations. When the tool approaches the workpiece and engages compliance, the path should not approach the edge head-on and then begin to move along the part edge. The tool path should blend into the edge, which will create the best possible finish. In other words, you want to merge onto the highway. You don't want to come to a stop at an intersection and then turn. This blending or merging accomplishes two things. First, it avoids abrupt contact that can damage the media or bearings on the tool. Second, it creates a much smoother finish. A perpendicular approach allows the media to dwell in one location, gouging that spot, while merging spreads that contact out across more of the edge. Another important consideration when programming the robot path is engaging the compliance in the middle of its travel range. Your path should be programmed such that the tool rides along the standard edge of the part with the spindle compliance at 50% of its total available travel. This way, you can account for high spots on your workpiece as well as low spots while maintaining contact. We have created this card to demonstrate where the spindle is in its compliance travel range. With the motor turned off and compliance air turned on, place the card against the part where the burr makes contact with the part edge. Pull the spindle away from the part and note where that side of the burr that was touching the part falls in this red and blue gauge. If your path is programmed correctly, it should fall right where the blue and red regions meet. If the edge of the burr is in the red region, your path is too close to the part and you risk bottoming out the compliance. At that point, the tool cannot comply any further and you have hit a hard stop. The tool effectively becomes a rigid spindle and all the force is being taken by the bearings, which can cause premature wear. If the edge of the burr is in the blue region, your path is too far from the part and you risk missing low spots because the tool is no longer in contact with the workpiece. This will likely result in an inconsistent finish because the tool is not in contact with the lowest sections of the edge. For a quick reference, you can quickly check that your tool is at roughly 50% compliance by going through your teach points with the motor off and stopping every few inches. Pull the spindle away from the edge. If your tool can be pulled off the edge, giving a gap of about 3/16 of an inch, then you are probably at around 50% compliance. For our axial tools, this distance is 1/4 of an inch. The last note on programming is to remember that complex motions are challenging to program. If a part is difficult for humans to deburr or grind due to complex movements, it may be challenging to program on a robot. Any tricky flicks of the wrist or large orientation changes must translate into robot motion. Keep this in mind as you choose which parts will be automated. It may be possible to automate everything, but the return on investment may not be as reasonable if it takes a long time to program and perfect. I hope this video has helped you understand how to improve your material removal cell.